In the last lecture, we saw how we can calculate the emissivity and absorptivity of gases based on information from each of the absorption bands of the gas. Today, we will take an example of how we can solve a real problem given the emissivity of absorptivity of gases. So, we recall emissivity of gas depends upon the path length of the absorbing gas and the gas temperature, and is defined as absorbent coefficient times the length scale there. So, this quantity, the integration of wavelength of the absorbent coefficient, has to be done by somebody, and here the path length is nothing but the total amount of the absorbing gas that is there along this path, and this is usually measured in kg per square meter or grams per centimeter squared in the older system of units. So, if somebody can provide information about how this emissivity varies with path length for different temperatures, then we can fit a function. So, we can make epsilon a function of temperature and u, and once this quantity is specified and available to you, you can then utilize this in solving the actual problem in radiation heat transfer. Now, let us see how we convert the problem which we had earlier defined in terms of absorption coefficient to one in terms of emissivity. So, in terms of the spectral values, if you recall, if we have, let us take a surface and this is the distance z from the bottom, and let us say you go up to some upper level and the total length is L. Now, after using the kernel approximation, we can write down the, assuming both surfaces are black right now. So, we will get sigma T 1 to the power of 4, this T 1 let us say, and this T 2. So, you have e to the power minus 3 by 2 after using kernel approximation. This is the flux downwards from the top surface. Then you had the emission from all gas elements between 0 and z. And finally, all the downward emission from all the gas element above z, E lambda be e to the power of minus 3 by 2 a lambda into z tilde minus z. Notice that always you are ensuring that this thing is positive, because it is the decay of the flux due to absorption. Now, we want to convert this equation, which is in terms of a lambda, into one in terms of emissivity, because we want to ultimately calculate q r, which is nothing but 0 to infinity q r lambda d lambda. So, we do the wavelength integration and we utilize the fact that total emissivity of a gas epsilon is 0 to infinity 1 minus a lambda z e lambda b d lambda. Therefore, delta epsilon delta z would be equal to 0 to infinity a lambda e to the power of minus a lambda z e lambda b d lambda. So, if you go back to the previous equation, I must remind you that the a lambda is here, which I did not include. So, you can clearly see that you can replace this by 1 minus epsilon after wavelength integration, and these can be replaced by d epsilon dz. Okay. And finally, we are going to use u, assuming homogeneous medium. We can define this as and the maximum amount of you can keep it general if you want. You can define this as so, this is the total path length of the absorbing gas, and this is the this is a variable, this is a parameter. Now, using this definition of emissivity and the derivative of the emissivity, path length, the total path length, we can rewrite the original equation now as follows. Notice that the argument in these functions is the distance over which the photon has to travel for reaching a certain level. So, that quantity will be u for the lower surface and u 0 minus u for the upper surface, that is, this is u 0, this is u and this is 0. So, when radiation comes from surface 1, it distance is u, and comes from surface u 0, it is u 0 minus u. Okay. Then you have the gas emission terms. So, now you find that the equation of radiative flux after integration of wavelength has been written in terms of emissivities. And so, the only task is, if we know epsilon as a function of u, then the problem is very well defined. Okay. Then we can solve for T g as a function of u, or ultimately T g as a function of z. So, the question is whether we have ready made data available for the variation emissivity of path length. Now, the answer is that it is not always available, but for certain well known gases like water vapor and carbon dioxide, people have taken the trouble to make laboratory measurements of the variation emissivity with path length and have fitted functions to it and made it available for the use by the wider community. So, if such data is available for the range of path length values that you are dealing with in a given situation, then it is possible to use this emissivity method. So, emissivity method for solving non-gray problems is feasible if somehow you can get hold of the exact nature of the variation of emissivity with path length. So, we are going to take, and we know that emissivity varies as linearly as u for small u and varies somewhat like log u for large u. So, this we had already discussed. These are the typical values in the limit of very low path length and very large path length. We also saw there is an intermediate region where it varied as square root of u. So, knowing the given situation and the range of u that you are going to encounter, you can think of some function of this emissivity, which is either from laboratory measurements, or we can also compute them from basic spectroscopic properties. Today, because of the availability of high speed computers, you can take the actual spectroscopic data for the various lines in the rotation vibrate rotation band and do the integration, and one of the method we discussed last lecture was the correlated K method. So, any method can be used through band absorptance or correlated K, and you can generate your own functional dependence of emissivity with u. So, there are various avenues available. Now, we will discuss one application of this problem. And I will say the application is to understand a phenomena called the lifted minimum. This is a very interesting phenomena observed in the atmosphere a long time ago, and had remained a mystery for a long time, because it is a result which, when it was first discovered, was not believed. Now, let us look at a clear night when clouds are not plainly rolled. So, on a clear day on this side, the surface temperature of the earth will reach a very high temperature, and you will see a sharp temperature, maybe this will go to 40 or 50 centigrade, and the temperature will fall rapidly with height. This is the height here. So, during the day, if it is clear day, the surface of the earth gets heated up very much and can reach temperatures ranging 40 to 50, but the air next to it will be at a somewhat low temperature, and you will see a rapid fall of temperature with height. But as soon as sun sets and the air is clear, then the temperature of the ground starts falling rapidly, and ground is a good emitter. So, it will cool rapidly. Air is a poor emitter, and hence very soon the temperature of the ground will be much lower than, depending on the place you are, it can even reach as low as 0 degree centigrade in winter. So, the ground remains the coldest spot because it is a very good emitter, and the air, which is not such a great emitter of radiation, will not cool as much. So, this is well known that the ground has the lowest temperature during clear nights, and this has been documented in many places in the world. But around 80 years ago, a discovery was made in India, which was counter to the simple understanding of the way temperature varies near the ground. Everyone assumed that ground will have the highest temperature during the day, which is not surprising because it absorbs directly the sun's radiation. And also, since ground loses heat rapidly, they expect the ground to have the lowest temperature at night. But the observations that were made both in Agra and Pune in 1931 by Ramdas and Atmanathan came as a great surprise, because when they made measurements of the temperature variation with height in the lowest 20 meters of the atmosphere, this region, they found that ground was at around 13 degrees centigrade and the temperature fell by about a degree in the first 2 meters and then started rising. So, the minimum temperature was not at the ground, but about a meter or less above the ground, and this was observed in 2 independent places, one in Pune and one in Agra. And this caused a great surprise when it was first published, because people asked how come the ground is warmer than the air when ground is such a good emitter. Why is it not able to cool rapidly to very low temperatures? And this behavior is not seen on all days. Only on certain days do they find the minimum temperature to be there above the ground and not at the ground. In most days, the lowest temperature is seen in this way at the ground. It will go this way, and only on certain special days does this unusual minima above the ground, called the lifted minimum, appears. This result is counterintuitive, because on all other days the temperature minima occurs at the ground. Now, this issue is of course of great academic relevance to understand phenomena, but it also has some relevance to the real world. If the lowest temperature appears not at the ground surface, but about a meter above it, then this has relevant to agriculture, because if there are vegetables or other things at this level, and if the temperature goes even lower, let us say to around 0, then there can be frost formation and damage to the vegetable. So, it is a problem which need to be understood, and one important criteria that was noticed is that this feature of the lifted minimum appears only on calm, clear nights. On windy nights, windy clear nights, you get the traditional minima at the ground, but on calm nights this minima shifted to about 10 centimeters or 1 meter above the ground. And the question is, what phenomena controls and the occurrence of minima not at the ground, but some centimeters or meters above it. Initially, various arguments were given. Some people argued that maybe there is a dust layer near the ground which enables the air to cool more effectively because of the presence of dust. But in many of the observations made both in India and also later abroad, there was no indication of existence of dust layer. The other possible reason people thought was the role of turbulence. They thought that on calm clear nights, turbulence may have been very low, and it could have led to a very unusual behavior of the eddy diffusion coefficient of turbulence to have some unusual feature which leads to this minima. But this hypothesis was not well supported by observations, because on calm clear nights normally one finds very little turbulence. Air is so still that turbulence generally does not exist on those days. So, if turbulence was not important and dust had not been observed in these locations, then one must attempt to explain this phenomena through a combination of radiative cooling and heat transfer by conduction. So, that is the only possibility one can imagine, that there is some interaction between conduction heat transfer near the ground and radiation heat transfer, which somehow leads to this interesting feature. So, this problem, in order for you to solve it, you have to set up the basic equations for conduction and radiation, and solve this problem. So, here it is shown how in this case you can write down the downward flux of radiation from the atmosphere integrated between u and what is called u infinity here. So, this is the downward flux from the atmosphere downwards, and the upward flux, if you assume the surface of the ground is not a black body, but a gray surface, then you have to worry about the emission of the surface as well as the reflection of the radiation coming to the ground. Okay. And this is transmitted finally to the level of interest. And this is the emission by all layers between surface and the level u, where emissivity is as usually defined in the traditional way. See a small difference in the way the pathline is defined. The pathline is defined as rho water vapor times dz. We also have added what is known as scaling approximation. In the Earth's atmosphere, pressure does decrease with height, total pressure. So, that will have an effect on the line width of the absorption band. So, you want to account for this non-homogeneous path you are dealing with. So, the traditional definition of path length is modified for this case by this expression of p z prime p 0 to the power delta. And so, this takes care of the non-homogeneous path followed by radiation as it goes from surface to very high altitudes. Now, the emissivity that appears in these equations can be fitted into two results, both involving logarithmic function, and one is for values of path length below 0.01 kg per meter squared, and the other is those with path length above 0.01 kg per meter squared. Now, these equations and numerical values are obtained by fitting laboratory data to obtain these values. Now, how good are these values? So, here is a plot of the emissivity of water vapor as function of the path length of water vapor. Now, in the outer figure here you see water path length going from 0 to 10 kg per square meter, and the emissivity rapidly increasing in the first few centimeters and then gradually increasing to a high value after a large path length. And in the inset here, we have shown variations over a very small range from 0 to 0.08 kg meter square, and you can see that this shape repeats itself when you even look at a smaller scale. Now, the interesting thing about this result for water vapor is that it is not a strong function of temperature. So, emissivity of water vapor at room temperature is essentially independent of temperature, so that we can use a single function to represent all cases that we are going to deal with. In addition to knowing the emissivity variation with path length, we also need to know how the ground temperature varies with height in the atmosphere. In the absence of radiation, the equation for temperature variation in the ground is a simple diffusion equation, which many of you have seen. To solve this equation, you will find that the temperature surface is going to decrease as square root of the time. This is time here. Okay. So, this was obtained from actual observations of the temperature of the ground at night for a period of about 12 hours. This by solving the diffusion equation in the ground, and this result we will see later on is very useful. So, now let us look at how this equation is solved. So, we solve the transient equation for the atmosphere. So, the transient equation for the atmosphere involves the unsteady term, the molecular diffusion term, and the radiative cooling term. For this calculation, we are going to use the emissivity model. And we saw that we had expression for emissivity as A log 1 plus. Let me just show again the expression for emissivity. So, now we knew that logarithmic function emissivity which we saw, and we will solve for this equation given this logarithmic function. And just as a reminder, this logarithmic function for epsilon was of this kind. Okay. And from a laboratory data, one could get values like epsilon u equals 0.049 log 1 plus 1263.5 into u for u less than and equal to 0.056 . So, this is a piecewise continuous function. Emissivity has a certain value below u upon 0.1, and at point naught 1 the slope changes, but not the function. Function will be continuous, but slope is not continuous. So, this was used in this equation, wherein the dqr dz was obtained from this equation. So, we have dqr by du calculated from this equation, emissivity has been specified, and this differential equation is solved for temperature at the next time step. So, this is a purely stepping procedure, but still certain care is required while during the numerical integration in ensuring that you maintain fine enough mesh in a region where you expect to see the minima. So, this kind of equation is fairly easy to solve today because availability of high speed computers. Now, let us look at what these solution equation tell us with regard to this phenomena. One example of this solution, starting with this near isothermal profile at time t equals 0, and then you integrate in time. Remember that even time t is 0, there is a very sharp slip here, and this is not surprising because during the day the sun heats up the ground to very high temperatures. So, at sunset you would expect to see a sharp temperature gradient between the gas elements away from the surface compared to those near the surface. But after about 1 hour, you can see immediately that the temperature profile has a minima at around a height of 10 centimeters. The agreement between observation and simulation is not perfect, but the shape of the curve is reproduced quite well. And at 2 hours, you can see that the temperature air near the ground is indeed lower than the surface temperature. So, what this shows is that we have been able to use the simplest model, non-gray model, which is the emissivity model, to correctly get the variation in temperature with height and now the question we want to ask is, now that you are able to reproduce that, we need more understanding of this feature. Now, here are results which indicate how the height of the minima and how the depends upon the cooling rate. So, if you look at it is a very high cooling rate of the ground, then you are not going to see much of minima, because ground cooling will dominate the entire picture. On the other hand, if ground cooling is low, then you can get a situation where you can get elliptic minima. Now, to really solve the problem exactly, you need to solve the problem in the ground here, along with the temperature profile in the atmosphere. So, let me just illustrate that briefly. So, the point is that we can solve this problem two ways: either specify the variation of surface temperature with time and one way that has been done earlier is to assume that the ground temperature falls as the square root of T, which is quite a reasonable approximation. Or if you do not want to do that, you solve the ground and atmosphere as a coupled system. So, you solve both for the temperature of the ground as well as of the atmosphere. So, this is a more realistic solution, and we see such a illustration of this coupled solution. So, here is the ground about 0.2 meters deep ground has been shown here along with the atmosphere, and these are the various solutions for the atmospheric temperature profile for various ground emissivities. So, one can see that if ground emissivity is quite large, close to 1, then you will not really will see a real lifting minima. Okay. On the other hand, if you assume emissivity of 0.9, you can get a temperature profile in which the minimum temperature is around 1 to 2 degrees below the ground temperature. So, we are able to reproduce the lifting minimum phenomena in the computer simulation, and it compares well with a simulation in which the ground temperature was not calculated. So, here you can solve for both ground temperature, air temperature and the atmospheric temperature near the ground together. Then you see that lifting minimum will be very strong and visible only if the emissivity is 0.9 below. At 0.9, the minimum occurs at 0.3 meters. So, you can see clearly here how the temperature of the ground is not cooling rapidly enough, while air is cooling more rapidly. So, both air and ground start at 300 degrees Kelvin, almost isothermal atmosphere. Once the air starts cooling near the ground, it sets up a very stable layer above, and the cooling is controlled mainly by what is happening near the ground. And here are a few more examples showing that the observed temperature profile near the ground does have a minima, and our numerical solution is able to capture some, if not all, features of this phenomena. So, precise agreement cannot be expected, but the general shape of the curve follows quite closely what is observed in the field. Now, next we will look at how some of the parameters of interest to us vary with ground temperature. This is the typical variation people assume, which is, as you saw, one of a bad approximation, but they also are calculated for various degrees of minima. But the key point you have to notice here is that as the ground cooling rate becomes larger and larger, the minima approaches 0. So, lifting minima can occur if and only if you have a calm, clear night, and if the ground cooling rate is not very large, then we can get a minima about 3 degrees Kelvin below that of the ocean surface, while if the cooling rate is very high at the land, Huh? So, what this solution of the combined conduction radiation problem told us was that the existence of minima depends both on the ground cooling rate as well as the emissivity of the ground. So, we will write down the important conclusions as follows. So, the emissivity model told us the following. It told us that the lifted minimum occurs 1, ground emissivity is less than 1, 2, ground cooling rate is not too large. So, which means that the ground, if the ground cooling rate is large, the minimum temperature will be the ground, but if the ground is cooling slowly, then it is possible for the atmosphere to cool more rapidly than the ground and to reach a temperature which is lower than the ground. That is the requirement. And the second important point that came out was that the emissivity of the ground has to be below 1. Now, this is a result which was initially not foreseen, and this result shows the important role that the ground emissivity plays in this phenomena. And this also partly explains the situation that occurs, why this situation occurs somewhat rarely. The lift minimum phenomena is not observed all over the world. It is observed only in certain conditions. Of course, one of them we discussed already is very low wind, because slight amount of wind will create turbulence and mix the different layers, so that the minima will disappear. And this has been shown when minima are occurring on a calm clear night. If you take a stick and just wave it in front of you, the minima will disappear, because minima can occur only in the absence of turbulence. So, even slightest amount of turbulence will mix the layers up and remove the minima. And to understand the role played by the ground emissivity, we must look at the expression for radiative divergence, which will be shown to be of this form. In this equation, for the divergence of the flux, so it should be quite clear that the divergence of flux has to be quite large for the lift minimum to occur. And so, if epsilon g is 1, this term is small, this plays no role in our analysis. Now, if this term has to be large, then epsilon g equal to 1 means there will be no cooling. So, the requirement is epsilon g should not be equal to 1, and the total emissivity of the whole column also should not be equal to 1. That means, there must be some scope for the layers near the ground to cool to space through the regions where atmosphere is fairly transparent. And the most important thing is the role played by the derivative of emissivity. Now, near the ground, this is the quantity of interest. And if you go back and look at the figure we saw earlier, that near the ground there is a slip, which is a phenomenon which occurs in radiation, and the slip depends on the emissivity. If the emissivity is close to 1, there is no slip near the ground. As the emissivity decreases, the slip becomes larger and larger, and this slip is a basic requirement for minima to occur. The ground has to be warmer by a few degrees with reference to the atmosphere for the minima to manifest itself. So, this shows the important role played by ground emissivity in controlling the radiation slip. Now, you can see that the radiation slip is somewhat modified by the conduction heat transfer, and so very close to the ground, this phenomena which is shown in greater detail here. So, this slip is ultimately diffused by the molecular conduction to give you a minima at a height of anywhere between 1 to less than a meter in this case. Starting with isothermal atmosphere, we are able to get to atmosphere where minima somewhere in this case between 0 and 50 centimeters. And notice it is very close to the ground. That is why many earlier measurements made with somewhat cruder instruments, which did not quite get to the lowest 10-20 centimeters, may have missed the existence of this minima. So, this minima to be discovered, you need fine instrument which will go all the way to the ground to identify that feature. And so, we see that the two other requirements are very clear here, that the emissivity has to be reasonably low to create a large slip, and the ground cooling rate, if it is too large, that also essentially destroys the minima. The ground cannot cool very rapidly. That is why the conductivity of the ground does play a role. The ground, if it is a poor conductor of heat, then it will cool very rapidly, then you will get this kind of rates. On the other hand, the ground is a good conductor of heat, then it will not allow the surface to cool rapidly, and hence it will keep the value of this beta around this value, and then we can get fairly high minima. The second parameter we saw was height at which minima will occur. That also depends upon the ground cooling rate a lot. Of course, emissivity, as emissivity increases, the minima moves closer to the ground, and as the cooling rate increases, the minima comes nearer to the ground. Ultimately, it disappears, it goes into the ground. So, the height of the minima as well as the degree of the minima, how much cooling occurs, depends both on the cooling rate of the ground and the ground emissivity. So, this is an example which showed how a simple emissivity model of the atmosphere can explain a subtle phenomena like the Lifton minimum. But it must remember that this kind of result can be obtained provided you get accurate information about the ground emissivity. Earlier, one did not have high quality measurements of the ground emissivity, and so you need accurate data for epsilon of u for very small values of u. Remember, u were typically of the order of 10 to the minus 2 kg meter squared. So, these kind of data were not easily available, and hence people used emissivity values which are not as accurate as that has been shown here, and if you do not do that, then you go and get reasonable minima. For example, we saw that the delta T min is very much dependent upon the slope of the emissivity curve near the ground. This is a crucial parameter. Many of the older correlations for emissivity that were available did not have sufficiently high values of this quantity, and so that led to the impression that Lifton minima cannot occur. So, not only one had to use the emissivity model to unravel this phenomena, one also had to use extremely accurate data for emissivity. And today, of course, either we can depend on laboratory data, which are not easily available because it requires very tedious measurements of emissivity over various path length, and secondly is calculations, and these calculations can be from line by line codes or can be from correlated K method we discussed in the last lecture. So, or band absorbance models. All these can be used to obtain emissivity for the range of path length that you encounter in a given problem. So, in this problem we discussed in today's lecture, the path lengths are encountered very small, and one had to look for very special data to get the information. So, we will illustrate the role of emissivity in this model. In the next lecture, we will look at other application of emissivity data that is relevant to furnaces. One of the important applications of radiation heat transfer in engineering is to furnaces. So, we will show how emissivity data for gases can be used in estimating the efficiency of a power plant boiler furnace.